There is an ocean current in the Atlantic that moves warm water north and cold water south, and it has stopped before. It is called the Atlantic Meridional Overturning Circulation. Everyone calls it the AMOC. It is the main current system of the Atlantic Ocean and half of the global thermohaline circulation. It is made of two things: a northward flow of warm, salty water near the surface, and a return flow of cold, less salty water in the deep. Let us start with the claim you have probably heard, because it is wrong, and the correction is more interesting than the claim. The claim is that without this current, northern Europe would be as cold as northern North America, 15 to 20 degrees colder. That is generally considered incorrect because atmospheric circulation does most of the heat transport, not the ocean. The consensus is that the AMOC keeps northern and western Europe somewhere between 4 and 10 degrees warmer than it would otherwise be, depending on the area. 4 to 10 degrees is not a film plot. 4 to 10 degrees is the difference between a farm and a tundra. The AMOC carries up to a quarter of all the heat moving toward the northern hemisphere, and the Atlantic is the only ocean on Earth where heat flows northward across the equator. The engine of the whole system is salt, and the reason the Atlantic has enough of it is one of the strangest facts in physical geography. Warm water is less dense than cold water, so it floats. Salty water is denser than fresh water, so it sinks. Everything about this current is the argument between those two facts. In the tropics, intense evaporation lifts water off the ocean and leaves the salt behind. The remaining surface water gets saltier. Near the Arctic Circle, sea ice does something similar. When seawater freezes, it expels salt into the water beneath it. But the most important reason is geographic, and it is delightful. The moisture that evaporates from the Atlantic does not fall back into the Atlantic. The trade winds carry it west, across Central America, into the eastern North Pacific, where it falls as rain. And it does not come back because the Rocky Mountains, the Andes, and the Tibetan Plateau block any equivalent return of moisture to the Atlantic. So, the Atlantic quietly leaks fresh water to the Pacific, across a continent forever, and is left saltier than any other ocean. The Pacific, by contrast, gets so much rain that its surface water is not salty enough to sink more than a few hundred meters. Deep ocean water has to come from somewhere else. It comes from here. In the Nordic seas, that salty northern water cools, gets dense enough to sink, and forms what oceanographers call North Atlantic deep water. It then travels south along the bottom of the Atlantic. Around 80% of it eventually upwells in the Southern Ocean. By the time it comes back to the surface, that water is typically 1,000 years old. Which is also why this current matters for carbon. Water that has been in the dark for 1,000 years has not met the modern atmosphere, so it absorbs carbon dioxide hungrily when it surfaces, and the upwelling brings nutrients that feed plankton. The North Atlantic is the largest single carbon sink in the Northern Hemisphere. Now, the part that makes this more than an oceanography lecture. We know what happens when this system falters, because we have a detailed record of it faltering. In the 1980s, Willy Dansgaard and Hans Oeschger analyzed Greenland ice cores and found something nobody expected: 25 abrupt temperature oscillations during the last glacial period. They are called Dansgaard-Oeschger events, and the scale of them is hard to absorb. Greenland warmed by between 8 and 15 degrees over a few decades. And while Greenland warmed, the Southern Ocean cooled by an equivalent amount. Heat was not being created. It was being moved. Scientists call that the polar seesaw. When the AMOC is strong, the north warms and the south cools. When it is weak, the opposite. Many of those warm events were ended by something even more dramatic, a Heinrich event. Named for the marine geologist Hartmut Heinrich, these were mass discharges of icebergs from the Laurentide ice sheet, the ice sheet that covered northeastern North America, pouring through the Hudson Strait into the North Atlantic. The icebergs carried rock the glaciers had ground off the continent. As they melted, they dropped it onto the seafloor, a layer of continental stone lying in the middle of an ocean. Those layers are how we know. There is a belt of that debris running about 3,000 kilometers from North America toward Europe. For one of them, Heinrich Event 4, modeling puts the fresh water added to the ocean at around 2.3 million cubic kilometers over roughly 250 years. Enough to raise global sea level by around 2 meters. And fresh water is exactly what this current cannot tolerate, because fresh water will not sink. Dilute the North Atlantic, and the water that is supposed to sink simply floats. The engine stalls. The clearest case is also the most recent. It is called the Younger Dryas, and it ran from about 12,900 to 11,700 years ago. It is named after a small white alpine flower, Dryas octopetala, whose fossils are abundant in European sediments from that period. The flower is a thermometer. It dominates when it is cold. The world had been coming out of the last ice age. Forests were growing in Scandinavia, and then the northern hemisphere went back to near glacial conditions possibly within a decade. Greenland cooled by 4 to 10 degrees. In Europe, between 2 and 6. In Britain, ice fields and glaciers formed in the uplands and lowland areas developed permafrost. At the Greenland summit, the cooling took 3 years or less. 3 years. Not a slow slide into a colder world, a step change inside a single human childhood. But look at the global number because it is the most instructive figure in the episode. Net global cooling during the Younger Dryas was about 0.6 of 1 degree. While the north froze, the southern hemisphere warmed. Antarctica, southern South America, and New Zealand all got warmer. This was not the planet losing heat. This was the planet redistributing it, badly, from a European point of view. And the cause is still argued. The long-standing explanation is a flood of cold fresh water from Lake Agassiz, a vast glacial lake in North America, reaching the ocean with evidence for meltwater traveling down the Mackenzie River. But that explanation has a problem. There is no matching sea level rise for the period, and there should be. So, other ideas have emerged. A volcanic trigger has been proposed, and anomalously high volcanism immediately before the onset has now been confirmed in both ice cores and cave deposits. It ended as abruptly as it began. Warming over about 50 years, and the Holocene, our epoch, the one with agriculture and cities in it, began. In the 1960s, the oceanographer Henry Stommel built a very simple model of this system, a couple of boxes of water exchanging heat and salt. What it showed has shaped the field ever since. The circulation has 2 stable states, a strong one, like the one we have had throughout recorded history, and a collapsed one. And the 2 are not symmetrical. Push the system hard enough with warming or freshening, and it flips to the weak state, and then it does not come back just because you stop pushing. To recover, you would have to reduce the warming and freshening that caused the collapse in the first place. That asymmetry is what the phrase tipping point actually means. It is not a word for very bad. It is a word for not reversible by simply stopping. So where is the AMOC now, and how worried should anyone be? Here is the careful version. Climate change pushes on both of the levers this system depends on. It warms the surface water, and it freshens it, with melt from Greenland and with increased rainfall over the North Atlantic. Both make the surface layer more different from the deep layer. And the more different they are, the harder it is for water to sink. Reconstructions suggest that as of 2015, the AMOC was weaker than before the Industrial Revolution. There is genuine debate about how much of that weakening is climate change, and how much is the circulation's own natural variability over millennia. That debate is real and unresolved. What models agree on is direction, further weakening during this century. There is also a curious symptom already visible, a patch of the North Atlantic that has stubbornly not warmed while the rest of the world has. Researchers call it the cold blob. A weakening AMOC would lower average air temperatures over Scandinavia, Great Britain, and Ireland, the places warmed by the North Atlantic current. It would also accelerate sea level rise along the coast of North America and reduce primary production in the North Atlantic, less plankton, and less of everything that eats plankton. And a full collapse would substantially lower average temperature and the amount of rain and snow in Europe and would not be reversible. There is a smaller historical hint of this too. Studies of the Florida current suggest the Gulfstream was around 10% weaker from about 1200 to 1850, and that this likely contributed to the Little Ice Age. One last piece of perspective, and it is the one that belongs to this series. The AMOC has not always existed. For much of Earth's history, the Northern Hemisphere's overturning circulation happened in the North Pacific instead. It moved to the Atlantic about 34 million years ago at the Eocene-Oligocene transition, when the Arctic-Atlantic gateway closed. Which means this current, the one that makes Europe habitable, in the way Europe is habitable, is a feature of a particular arrangement of continents, and it is roughly 34 million years old. Some researchers have suggested that if the AMOC shuts down, the circulation may eventually reestablish itself in the Pacific, going back to the older arrangement. The ocean would go on turning over, it just would not be turning over here. That is the honest shape of this. Not a wall of ice arriving in a week. A large, slow, well-documented machine with a known history of switching states, which we are currently pushing on in both of the ways that make it switch. We know it has stopped before, because a flower and a layer of stone and a column of Greenland ice all say so. And we know what it was like when it did, because the last time it happened, there were people here to live through it.